In this lecture, we'll look at the difference between accessing an array by indexing it or by accessing it via pointers. And we'll also look at the performance implications of doing it one way or the other. So let's start by defining as a very simple function that we want to implement. This function is called the function clear. And what it does, it simply writes the value 0 in all the elements of an integer array. And again, we are assuming an architecture that's a 32-bit architecture, so each integer will occupy 4 bytes in memory. The parameters for this function, the first parameter is called array, and is the address of the first element of the array. And the second parameter is called size, that's the number of elements in the array. So here I have a drawing for my array, and in this drawing, my parameter array contains the address of the first element of the array, which is the element 0 of the array. And my array has size elements, so the elements of the array go from 0 to size -1. The position array size is not part of the array. This contains something else in memory. So let's look first at accessing this array via indexing. So this is the typical sub-I that we use for accessing an array. So my index I, if I put in a number line, I will initialize my index with the value 0, and I will increment it by 1 in each iteration of the array. And I will stop the loop when the value of I is equal size. Now, to index the array using pointers, remember that the first parameter of my functional array contains the address of the first position of the array, or the position 0 of the array. So I'll create a pointer P to access this array, and my stopping criteria now is no longer size because I'm not incrementing the pointer P by 1. My my sentinel to terminate my loop will be the base of the array size plus size, the base of the array plus size times 4, which will be the address of the position after the end of the array. So P will initially point to the first position of the array, so I'll make a copy of array into P. And array plus size times 4 is the position after the end of the array. So my number line now will not gonna contain integers from 0 to size. My number line will contain addresses, memory addresses, and let's suppose that I start at the address 1001.0000. So this is the address for this position in memory. The next position of interest to me is the position of the next element of the array, which will be 4 bytes after the first position. So I'm going to skip 4 bytes, and the next position will be 1001.004. The following position will be 1001.008. And at some point, I'm going to get to the last position, that is where my stopping criteria are going to be. So my increment in the case of the pointer will be an increment by 4. So every time that I do an iteration of the array, I increment by 4 until I get to the position that's the last position of the array. And by doing that, I'm going to write the value 0 in every position of the array. Let's look at the C code. The C code for the first version of my function is called clear1. And the first parameter for this function is the address of the position 0 of the array, which in C notation can be represented as int array and open close square brackets to indicate that this is a variable that contains the address of the first position of array. And the next parameter is size, which is an integer value that tells me how many elements are in the array. I'll have a local variable I that I use to index the array, and I will initialize this variable to 0, And remember that before I do any iterations of the loop, I need to test it to see whether I is less than size. Because I could have received the value of size that was 0 or even negative in this case, because the type of size is integer, and I do not have unsigned in my C code, so I could receive a negative value. And my increment is by 1, and the body of the loop is very simple. It's simply the assignment of the value 0 to the position y of the array. So I will have array will be in register A0 because the first parameter of a function comes in register A0. And my local variable y, I will allocate to the register T0 for it. And remember that size will be in A1. So if I do a pseudocode for this implementation, for this code, what I will do is I will initialize T0 with 0. And then while T0 is less than size, I will increment, I will compute the address of array sub I, which is computed by multiplying T0 by 4 and adding to the base of the array. And now I will access the memory position at that address. Remember that this notation we use in pseudocode to indicate that I am writing to the memory position. I'm writing because it's on the left-hand side of the arrow. I'm writing to the memory position whose address is T2. Memory, as represented in this pseudocode, is an array of bytes. So I do not need to multiply T2 by 4 in order to find the memory position. T2 already gives me the address of the word where I need to write the value 0. And then I'm going to increment T0 by 1. As we know, we cannot multiply by 4 and add in one instruction. So to make the pseudocode closer to the assembly, we're going to replace this statement here with two statements. The first one will be the multiplication of T0 by 4, and the second one I'm going to add the result of that multiplication into to the base of the array to obtain the address T2 that then I use for my memory access. My store word will be using that address. Now let's look at the pointer indexing version of the same code. In the pointer indexing version, my first parameter is int star array. This is just to indicate that I work with pointers. In C, the syntax that says int star array and the syntax that says inter array open close square are identical. They do exactly the same thing. My second parameter is still the size, but now my local variable is not an integer I. My local variable is a pointer to an integer, and I call this local variable P. The initialization for my for loop is I will assign the address of the first position of array to P. And I'm using on purpose this notation here. I could simply say P equal array. But to make the program more legible, I'm using this notation that says I take in the address of the position 0 of array. And then I will have computed the address of the position size of array. Remember, the position size of array is outside of the array. The last position of the array is size minus 1. So I take the address of the position after the last, and I will remain in the loop as long as the pointer P is pointing to a memory address that is smaller than that address. And my increment is by 1. This might come as a surprise because we said that in the case of a pointer, I need to increment the pointer by 4. So how come that in the C code, I'm incrementing the pointer by 1? What happens is that the C compiler, whenever you increment a pointer, the C compiler is going to go and check what is the type that that pointer points to. In this case, this pointer points to an integer. We are in a 32-bit architecture. We know that an integer is 4 bytes. So the compiler will automatically replace when generating the code this increment by 1 by an increment by 4 to make it correct. And inside the loop, all I need to do is to say that the memory position that's pointed by P should receive the value 0. So again, for my implementation, A0 is the array, and I'm gonna now my temporary variable T0 contains the pointer P. A temporary variable or any other register may contain a value, such as in this case, it contains the value of I, or may contain a memory address that both of them are 32 bits. So my pseudocode here now, I'll first initialize my pointer P that is in register T0 to the address of the first position of the array that I can represent simply as array. Next, I need to compute the address of the position size of array because that will be my sentinel for my loop. That will tell me when I'm done with my loop iterations. And I'll be repeating my loop as long as the pointer P contains an address that is smaller than the address of the position size of the array. And inside my loop, all I need to do is to do a memory access at T0 because T0, which is the pointer P, already contains the address of the memory where I need to store the value 0. And then I will increment the pointer. Now in the pseudocode, I represented that I'm implementing the code by 4 because this is what I'm going to have to do in the assembly code. So let's make a few observations about these two codes that we just generated here. The one on the left was with based on array indexing. The one on the right is based on pointer indexing. The first thing to note is that in the case of array indexing, I must multiply by 4 and I must add the result to the base in every loop iteration. So this will be adding to the work that I have to do. Now, if I look at my version for pointer, the pointer already corresponds to the memory address that I need to access, and I do not need to do the address computation that I need to do in the code on the left. So if I now create my assembly code, the first thing that I need to do before I even get started in the loop is to test the condition to see if n is less than or equal than 0. If n is less than or equal than 0, I'm done and I should not go into the loop. Otherwise, I'm going to initialize I to 0, and then I will multiply I by 4 and I will add it to the base of the array that is in A0 to obtain the address where I need to access memory. I will store 0 in that position, and I will add 1 to the index I, and I will test to see if I is less than size. If I is less than size, I'll go back to the loop. Here's the code for my pointer version. In my pointer version, I also gonna first test to see whether n is less than or equal to 0, because in that case, I will terminate the loop. Then I will compute the value of the, I'm going to assign the value of the array 0 position to the pointer P, which is T0. And then I'll multiply the value of size by 4 because I'm doing the address computation for the position of array size. That's the position after the last position of the array. And I'm going to go into a loop. In my loop, I will simply store the value 0 in the position of the array given by the pointer and increment the pointer by 4. And now that I have done that, I'll test it to see if I should remain in the loop. And I'll go back to the loop if I'm done. So if I look at these two codes and I count the number of instructions, I have 7 instructions on the left and I have 7 instructions on the right. So on the surface it appears that those two codes are of the same length. But do they execute the same number of instructions? And do they consume the same amount of time? So to decide on that, let's make an assumption here that my add I, SLI instructions all take 1 cycle. And I think I also made the assumption that my branch less than equal will take one cycle. It could be two cycles. It doesn't make a much difference for this calculation, as we're going to see. My start word is 5 cycles, and my branch less than is 2 cycles. So with this assumption, and then we're going to assume that the size is very large, which means that the number of times that I execute the loop is much larger than the single time that I execute the instructions that are outside of the loop. The question now, which of these two versions of the code is faster and by how much? So if I assuming that this branch takes one cycle, I may change these slides later and make them take 2 cycles so that it takes the same time as the branch less than. But for now, let's assume that this is 1 cycle. So I have 1 cycle for the branch, 1 cycle for the move, 1 cycle for the shift left, 1 for the add. I have 5 cycles for the store, 1 for the add, and 2 for the branch. And here's something similar, so I simply annotate my code with the number of cycles that each instruction takes. So now I can do my computation by saying I can count the number of instructions executed. So this version of the code will execute the instructions that are inside the loop size times. And so the value here is 5 times size, so because I execute these instructions size times, and the instructions outside of the loop are executed 1 time. So I have 2 cycles outside of the loop in this assumption that I made. Now, what's the number of cycles that 2 instructions. What's the number of cycles that I execute? I execute 1 and 1 outside of the loop. And then inside of the loop, I execute 1, 1, 5, 1, and 2. So the number of cycles will be 10 times size, that's adding the value in here, plus 2. So if I want to compute the CPI now, the CPI will be the total number of cycles that I need to execute this code divided by the total number of instructions. So I have 10 times size plus 2 divided by 5 times size plus 2. This gives me approximately 10 over 5 when the value of size is very large, which gives me a CPI of 2. So this code executes on average, needs on average 2 cycle clocks per instruction to execute. Now let's look at this code here. I did a similar computation, but now I have 3 instructions inside of the loop. So it's 3 times size plus 4 is the number of instructions. And the number of cycles will be 4 plus size times 5 plus 1 plus 2. That are the cycles for instructions inside the loop. So the number of cycles will be 8 times size plus 3. And then so this should be plus 4. I'll fix this slide later after the video. So the CPI here will be 80 divided by 3 when size is very large. Notice that what happens outside of the loop doesn't matter when size is very large. So when I have a very large array. And the CPI here is 2.67. So notice that the CPI, the number of clocks per instruction in this version of the code is higher than the number of clocks per instruction in this version of the code. You may stop and think for a bit to try to think about why is that the case. And you're going to realize that that's the case because in this version, the loop is executing 3 instructions that take 1 cycle and 2 instructions, one with 5, the other with 2. In this version of the code, the loop is executing only 1 instruction that takes 1 cycle and is still executing the 2 instructions that takes 5 and 2. So if I just take the number of clock cycles and divide by the number of instructions, I'll see that the CPI here is higher. So if I just consider, if I just think, having fewer clock cycles is better, so a lower CPI is better, I may say that the loop with the array indexing is better than the loop with the pointer indexing. But is that the case? Let's look at the number of clock cycles overall for these 2 codes. The index is executing 10 times size plus 2, and the number of clock cycles for the pointer version is 8 times size plus 4. When I divide this, I'll find that the pointer version is actually 1.25 times faster than the index version. So even though the pointer version has a higher CPI, it is faster than the index version that has a lower CPI. So if I compare the array index versus pointers, what I see is that the array index requires a shift to be inside the loop. That's to compute the multiplication by 4. And that shift is part of the index calculation for the incremented I. And I need to recalculate the address at every iteration of the loop. A compiler can achieve this, can get the same effect as you do using manual pointers. So this lecture is not about recommending that your C programs you always use pointers. Pointers might be actually harder to maintain and to reason and to read the code. So there is nothing wrong with using indexes in your C code, because a good compiler will achieve the same effect by applying an optimization called induction variable elimination. So with that optimization, what the compiler is going to do is the compiler will automatically remove your indexes and replace them with pointers to save the address calculation. So in general, it's better for you to make your program clear and safer, so that if either yourself or someone else maintaining the program in the future will not make mistakes, and then leave for the compiler to make your code efficient.